First, I'd like to thank the organizers for inviting me to this wonderful conference. It's my first time at QEC, and I'm really enjoying all the talks so far, and I'm looking forward for the rest of the talks. I'd also like to thank the funding agency, both IARPA and LPS. A lot of the work I'm presenting today was funded by them. So I'm Maika Takita from IBM Research, and my title is fairly broad, vague. It's exploring building blocks for topological codes with superconducting qubits. I decided to add topological and subsystem codes since a lot of the near future work that I'll be talking about kind of includes the subsystem codes. But what I really mean is just, okay, how do we do RRC NOT gates, the 2 qubit gates, and the measurement, and reset or initialization. And individually, we could show that we could do these in small systems, but as we bring all the qubits, multi-qubits together, what are some of the issues that we have? If you just consider not only these small systems, but in the large-scale devices. So this is my outline. I will start telling you about the quantum system that I work with. It's the transpond qubits, superconducting qubits, and how we run our quantum gates. Hold on, let me just do this. And then I will move on to telling you a little bit about the small codes experiments I have run. It's mainly the fault-tolerant and state preparation and how we do this wait for parity checks. I will then move on to describing what's necessary to do these syndrome extraction, where you need to do fast state determination and ancilla reset. And what classical electronics that's necessary to realize this. So at the end, I'm going to kind of talk a little bit about the issues not issues, but the fixed frequency transpond inherent frequency collisions that we have in our device and the difficulties that we have in making these larger devices with lots of connectivity. So the outlook in the surface code that we have been looking at. And I'll introduce this new topological and subsystem codes that the members from our team, the theorists, had come up with, and just kind of discuss where we are in terms of the theory and also with the experimental work related to that new code. Okay, so transpond qubits. So most of you probably have heard of or seen this slide or heard about this somewhere or another, but the anatomy of superconducting qubits. So this is one of the IBM Q Experience 5-qubit device. If you just focus on to the qubit and the resonator, I'll just discuss about this resonator first. So this is a superconducting microwave resonator. We use this as here for our quantum bus, and also the resonators are used to read out the qubits. So you could just think of this as just a simple LC oscillator, which gives you this harmonic oscillator. So here, because these spacings are equal, you can't use this as a qubit. But by using a Josephson junction as a nonlinear inductor, now you have an harmonic oscillator, and you can address the first 2 levels as your qubit. And now you have a qubit and a resonator that you could couple. So resonator plus qubit. Here's the circuit. This is Hamiltonian describing the interaction between the cavity and the qubit. And at the dispersive limit where the cavity frequency is detuned from the resonator from the qubit frequency, the cavity frequency depends on the qubit state. So this plot, blue is when the qubit is in the ground state. I'm doing a spectroscopy of the readout resonator frequency, and red is when the qubit is in the excited state. So as you see, there are two peaks, and they're separated by 2 chi. And this is telling you how strongly coupled you are to the qubits and the qubits and the cavity is coupled. Okay. So just looking at the multi-qubit system, now here's the older 4-qubit device. But just typically, we work with single junction transmons. These are fixed frequency junctions around 5 gigahertz. And we have our harmonicity of around 300 megahertz. And again, the coplanar waveguide as quantum buses, and also used for readout. That's usually around 6 to 7 gigahertz. And then we also have these ground planes. just to show how we actually mount the qubits and cool it down. Typically in these planar devices, this is an 8-qubit sample. We put it on a printed circuit board, just mount it in the dilution refrigerator. We cool it down to about 15 millikelvin and close it up. And at room temperature, we have all sorts of microwave electronics that we use to control the qubits. So now, how do we use these electronics to talk to the qubits? So quantum gates. What we'd like to do is control the qubit state and just drive around the block sphere by using microwave pulses. Typically, for single qubit pulse, we could do from 10 nanoseconds to 50 nanoseconds, around 5 gigahertz. And again, we use an AWG and the microwave source and mix it make these pulse shapes to control the qubits. So the pulse phase, just the phase of the microwave pulse, can correspond to the different axes of block sphere. So just by shifting by pi over 2, you can apply either x90 or y, x axis or y axis. And if you actually consider the phase gate, the Z gate is a special case where it's just done by the phase correction on the subsequent pulses, so it's actually free. So these we set it so that both X and Y pulses have certain gate lengths. It's a Gaussian pulse that we apply, and phase gates are all free. It does not take any time. So those were single qubits. So for 2 qubits, there are different ways of implementing 2-qubit gates, considering superconducting qubits. But because we have a fixed frequency transmon qubits, and with the qubits coupled to a bus resonator, I'm going to talk about this cross-resonance gate that we use. A good thing about cross-resonance gate is that we could use these fixed frequency qubits, and they tend to have long coherence times. The downside, they have these strict qubit frequency requirements. It only works in certain regimes. So a cross-resonance gate is an all-microwave entangling gate. And we have this static J coupling through this quantum bus that hybridizes the qubit levels. And by driving the control qubit, here's qubit 1 as a control, at the target qubit's frequency, you could drive this ZX or ZU rotation. So we use this coupling to make a C0 gate. So from about 8 years ago was the first time we demonstrated use 2-qubit gate using this cross-resonance gate. Back then we had about 80% gate fidelity, and now in the more recent years, we have a method to implement the cross-resonance gate, and we've been demonstrated a gate fidelity of above 99%. So now we know the system I'm working on and also the type of gates that is available. Let's talk about this fault-tolerant quantum computing via the surface code. So through the IARPA's MQCO and logic program, we have been working towards building a multi-qubit device and sort of focusing on how we could build a layout where we could run the surface code. And we like the surface code because there's the wait for parity operation, parity checks, and you only need to do some local operations. And these pieces, it seems to be not too demanding in terms of how we could have the layout for our superconducting qubits. So while we don't have enough qubits to actually run any surface code operations, when we actually made it up to 5 to 7 qubits, we thought, okay, we have a small system large enough to kind of start looking into what can we study about these fault-tolerant codes. And one of the codes that we looked at is this 5-qubit 422 code. We have this is a code with 2 logical states, and one of them is a fault. We could prepare it fault-tolerantly, the other not. But just to go over, I think this will be just review for everyone, but for the 422 code, the two stabilizers are the XXXX and ZZZZ. These are some of the logical states, the logical 00 to 11. And you have these two logical states, L1 and L2. And you could define the logical bit flips and phase flips for both the qubits. And just how you prepare the logical state, what I did was by measurement. So I run an X parity check and do a measurement on the syndrome to prepare the 00 state or whatever state that you want. And just looking at how the error propagates, so any single qubit errors are detectable. For example, say you have this phase error here with the Hadamard flips to X, and now you have an odd parity, odd number of errors. So once you run the Z check, you should be able to detect this. But there are some types of error that you can that would turn out to be an even parity error propagation. So for example, if you have an error here due to this hook error, you could have these even numbers of bit flips. This actually is a logical error for the logical 2 state, but it actually is not an error for logical 1. So it's the fault, so the fault tolerant state preparation circuit for the first logical 1, but not for logical 2 state. Okay, so you could prepare this 00 state, and just by applying these logical bit flips on first or second qubit, you can prepare all these other states. So the plus plus state, how I tried to prepare was again just initially prepare the logical 00 state and just apply Hadamards on all the gates to flip it to plus plus state. Just note that because we apply these Hadamards on all the gates, now the protected qubit engaged qubit has flipped. So the second qubit is now fault tolerant. So device characteristic on the 5 qubit device that I actually used. So this was the first IBM Q Experience 5 qubit device that we put up online a few years ago. And this is some device characteristics. We had T1, T2s of above 50 microseconds. And as I said, the qubit frequency is in the area of around 5 gigahertz with resonator frequency of around 6 gigahertz. So we all had just some JPC amplifiers to do a high fidelity readout. So just going back to the cross resonance gate. So now we have 5 qubit. These two qubits have this J coupling. When you drive the control qubit at the resonance of frequency of the target qubit, you drive all these different terms. What we're interested is in this ZX term. So while we have all these terms, we can apply some echoing scheme to get rid of most of the other terms. And by applying 2 cross resonance gate of the Pyro 4 rotation, we can get rid of all these terms except for IZ. And we could benchmark these gates to the gate errors of about 2.5%. So we use this gate as our C0 gate. And going back to the state preparation of the plus plus state, now I actually want to see how well I actually prepare the state. So again, this is the state preparation circuit. And after you prepare the state, I do a post rotation and look at the reconstruct the states. And these are just a notation. I'm going to define the syndrome bits as SZ and SX. Those detects the phase and the bit flip error. And you can look at this destabilizers is defined this way. And that changes the stabilizer eigenvalues without changing logical observables. So again, this is, I think, a lot of detail that you probably know already. So you could have this not in the qubit space, but just kind of I want to map it onto a 4-qubit Hilbert space with logical 1, logical 2, and the SZ-SX term. So that's easier to understand where we are in the code space. So go back to this circuit. So I run this circuit. I do a state tomography and make reconstruct the state. And this is the result. So here, I don't know if you see the axis, but the top left is the plus plus with the syndrome bits as 0, 0. So this is the state that I wanted to prepare. And in this yellow region, that's where SZ, SX are 0. So that means that we have, if you have done a parity check after preparing the states, that's where this will be the state where you would have accepted the state, whereas meaning there was this where we didn't have the error. So you see these points outside this yellow square, and if you actually look at the acceptance probability, that is the probability of SZ and XX being 0, it's less than 30%. So this is, I did a terrible job in preparing this plus plus state. So what's going on? So back to this cross-resonance gate picture. We have this 2-qubit gate, but there are all these neighboring qubits. I call them the spectator qubits. Because of how we couple these qubits, here I don't have the drawing, but we have 2 bus resonators. So D1, D2, the data qubit 1, 2, and the syndrome qubit are all coupled in the same bus, and then the same for the bottom 3. So while you're driving these 2-qubit gate, there are all these neighboring qubits that could be getting affected by the 2-qubit gate, most likely. So let's, considering the first and second order Z terms by including the spectator qubits, there are all these other terms that does not get canceled from this TPCX pulse sequence. So now we just make this into a full pulse sequence. Well, I'm going to call it FPCX. And by doing this sequence, now we could get rid of all these other terms that if the target, the spectator qubits, have had these phase errors. So then, again, similarly to how I normally benchmark the 2-qubit gates, I run a randomized benchmarking sequence, and you could get an error rate. This was a little high, but they were all less than 4.5%. Okay, so this was the state tomography result from when I created the plus plus state using the 2-pulse echo sequence, and are the results. And then now moving to the 4-pulse sequence, now you see that the acceptance probability went closer to 80%. And if you actually, you probably can't see, but there's some of the larger errors that you see within this accepted states are a bit flip, not a phase flip on the gauge qubit. So this state is the minus plus state, where the gauge qubit had gone to a minus state. So if you only look at the errors and comparing it with the protected to the gauge qubit errors, now we have about 1.3% error on the protected, whereas the gauge qubit error was about 0.27. So just to summarize, like the errors that we got from a protected versus gauge qubit, comparing the 2-pulse sequence versus the 4-pulse sequence. And here I have the gate errors from randomized benchmarking on those 2-qubit gates. I've only put the best error per gate and the worst error per gate. Remember, I had 4 2-qubit gates to run this code. You see that the error that we see on these logical states are much lower. So first, the acceptance probability goes up by introducing the spectator qubit echoing, so that's good. And then now the protected qubits has lower state preparation error than gauge qubit. So what else can we look at if we can do the state preparation? So what I looked at was to observe the decay of the logical 1-1 state. So again, I prepare the state by measurement. This is how I prepare the state. So I prepare a logical 1-1 state, and I just waited. So this here, I'm not doing any syndrome extractions, but this is just seeing how the logical state decay over time. So what we wanted to see, so here is the, an x-axis, the time that I wait versus the population of logical one state on both the protected and gauged qubit. Red is for the protected qubit and blue is for the gauged qubit. Just focusing on the first part of the decay, you see this little non-exponential decay of both states for protected and gauged qubit. And the key point is that we actually could get this fairly high, like y-intercepts. This is not possible if you don't have an actual fault-tolerant state preparation circuit. And the dashed line is the model, and this is consistent with just including individual amplitude damping of the data qubits, and also adding some readout error at the end. Okay, but so this is, I just did the state preparation and just waited. In reality, that's not what we want to do. We need to do repeated measurements to do the parity extraction. So for this device, I didn't have the capability to do that. So that for the next section, I'm going to focus on what type of things we have to consider when we want to do fast measurement. Okay, so just to review, we have a qubit device, put a readout tone, go through amplifiers, and look at the signal, and how fast you could read out get the information out of this depends on how strongly the qubit is coupled to the resonator and how strongly the resonator is coupled to the environment. So you need to push the kappa and also chi. So now this is the new device that I had made. It's a 5-qubit device to study a device where I had a central qubit, which is going to be the syndrome qubit, with higher chi and kappa. And when actually pushing these kappa and chi up, you have to worry about you have to filter against the environment. So we had to add extra filter on the resonator to protect the qubit from it. So just to characterize, the qubit that I'm focusing on is qubit 2, which is the one I'm going to do a fast readout. But just as comparison, where the things to compare is that the qubit 2 had about 2.5 megahertz kappa and about 5 megahertz 2 chi. And the qubit 3 is a fairly standard design, which usually comes out to 500 to 800 kilohertz kappa, and 2 chi is fairly standard. So this is similar to the previous device that I had as well, which had about 600 kilohertz kappa and 2 chi. So another thing to note is that even though we have increased the coupling, we still have similar coherence times to both T1 and T2. So this is looking good so far. So let's just talk a little bit about the classical electronics. The new classical electronics, the Fpga card that we have now, has a 2 DAC channel for the qubit control and also for the readout. And we also have 2 ADC channels for capturing and the readout signal. So this allows us to have this programmable instruction set to sequence waveform generation from local memory with deterministic latency. So this allows us to have them get the readout, read out the qubit, and then feed back to the following sequence. So this is the actual setup that I have. So here so this is not quite very important, but all I wanted to say was I'm using both the Fpga and COTS AWG to run these experiments. I could only just use Fpga as well, but this is how I had this experiment set up to run this experiment. So how we did the reset is, okay, you have some operations first. You do your qubit readout. And if the Fpga thinks it's 1, it's going to trigger the switch so that the pi pulse goes through. And then you could do another measurement to confirm that that actually did the job. So in the other case, with the Fpga thinks from the first measurement it's 0, it actually then opens a switch which doesn't allow the qubit pulse to go through. And then now it's not resetting the qubit to the ground state. So then you could then again measure the qubit to see what the state was. So this is a type of experiment I run. I do measurement I prepare the states in either a 0 or an excited state, do a measurement, you do a reset, measurement. And here, I have put down the probability of 0 state at each stage of the measurements. As you see, the first, when you prepare the excited state, if you first measure, there are very little ground state qubit, but after the first reset, it goes up. This readout histogram is just from a single measurement. This doesn't include the reset pulses. So if you just do a one measurement, which was 300 nanoseconds, I was able to get about 99.7 readout assignment fidelity. So just for the timing, how long it took to do this experiment was the measurement was 300 nanosecond. It took about 400 nanoseconds. That was used both for integrating and also the time to empty the cavity. And then at the end, another 50 nanosecond pulse to reset the qubit. Okay, so I'm defining the reset fidelity this way. And if you just get these correlated results from the previous number of previous results to the subsequent experiment, you could get these reset fidelities for each step. So the first time you do a measurement and a reset, the reset fidelity is fairly low. But then after that, it goes up to about 97, and it's fairly stable after that. So this first reset, it is largely from this probability of 1 given 1 when qubits are prepared in the 1 state, and this is dominated by the T1 error. So initially, you do a measurement. The Fpga reads 1, but by the time you actually apply the pi poles, it has actually decayed to 0, so then you actually flip it back to 1. But second time and third time round, there are much less number of excited state qubits. So these are for different experiments. But okay, so here is the Fpga latency budget breakdown. So at the moment, with the measurement pulse of about 300 nanoseconds and sampling a little longer, if you don't need to worry about getting the results and just moving on with the experiment, we could continue with the experiment at about 650 nanoseconds after the readout and some reset pulse, and then to continue. So this is the time. You need some time to empty the cavity so you could carry on with the experiment. With the classical electronics, if you actually want to use the information that from the readout results, there's a little bit of additional time that it's required, but it's not much. And just by we were setting it so that we were running in a measurement cycle of 800 nanosecond. From this setup, I could actually push it down to about 740. But I just added extra buffers just to make sure it was running properly. Okay, so back to the same picture of the quantum control. There's the classical electronics. So I will not be able to discuss about this much. Discuss about this part during this talk, but we have also implemented the branch conditions for pulse sequence. So we have this if then else go to sort of sequence, so that that's the. I guess I could just carry on with my talk. So using this, so in the previous experiment, all I did was reset the qubit. So we, it was just applying a pi pulse or not pi pulse. But there is also a way, using this FPGA card, I could do some conditional operations. So depending on the previous qubit results, I could choose to run a totally different sequence of experiments after that. So let me switch gears and talk a little bit about frequency collisions. So I'm going to describe some of the frequency collisions that we see from our superconducting qubits devices. But the goal is really to reduce the spatial correlation of errors on these devices. And this is a lot of information, but the key point is that, say here are there 4 qubits coupled to the same bus. say you're focusing on one qubit here, depending on what these neighboring qubits frequencies are, that counts as a collision. And you just say if this qubit J and this second qubit has the same frequency, you just can't use them just because we always have this always-on coupling through the quantum bus. So, and there's some bounds that we put. If it's too close, if it's exactly on the same frequency, you just can't use it. If it's far enough, there are certain pulses that you could apply so that you could individually address these qubits. But there are some good bounds where it makes the experiments much easier. So it's a collision with a direct frequency collision. It could also be a collision if it's only separated by unharmonicity over 2 or by unharmonicity. Depending on the frequency difference, that could make the cross-resonance gate run very, very slow, which is not great. So because we always have qubits, the qubits is just not 2 of them coupled, but there are other qubits that are coupled to the control qubit. You also have to consider about the frequency collision of non-nearest neighbors. So if these 2 qubits are coupled to the control qubit, you can't have them to be the same frequencies or have their frequency differed by unharmonicity. We also have this special case of the spectator error, where we don't want to have the F01 of these target qubits to be equal to the F02 of this control qubit. So this is kind of separate frequency collisions. So back to the surface code architecture. To run this wait for parity checks, you could consider having different number of buses that couples between the qubits. So you could think of having these grids where you only have 2 qubits per bus, and you still have each qubit would have 4 qubits attached to it. Or you could think of 4 qubit per bus. This is the type of device that I've been working on. The device I was working on would be, say, this one part where there are 2 buses and 5 qubits all coupled. With this 4 qubit per bus, there are up to 6 qubits that's coupled to a single qubit. So just by looking at this, you see that, okay, just from the connectivity and the frequency allocation, this might be the better way to go. And then even with this, you still need to ideally have 5 different frequencies to actually be able to run the qubits properly. But with currently from the fabrication, we just aim to have 1 frequency and just rely on the spread, the scatter about the mean of the qubit frequency that we target. So from this information, just want to have some statistical model on frequency crowding. So what we assume is that we have these transmon qubits with unharmonicity of 340. We choose the pattern of mean frequency, either 1 frequency pattern or 5 frequency pattern, and you could choose to have different sigma, which is limited by fabrication. And then you could count the collision according to the list from the previous slide, and you could do a repeat Monte Carlo style to build statistics. So here's the result from that. Let's just focus on these 2 red lines. These are from the 2 qubit per. The red line is if you did have 5 frequency pattern. You see that comparing it to this 4 qubit per bus, there's a 2 to 3 more collisions on this 4 qubit per bus design than the 2 qubit per bus, 2 qubit per bus design. So again, from this simulation, you could see that this has a little better. The y-axis is mean number of collisions, so you want to have much less. You could go lower. So this is from that you could say that the 2 qubit per bus design is better, but realistically, from the fabrication, where we have our sigma is around 150 to 200 megahertz. So we're kind of all the way out here. Now the y-axis is yield. So this is the yield for actually getting a 0 collision chip. And here, considering a 17 qubit device, which is going to be the distance 3 surface code architecture. So the yield is very low with the 150 or 200 megahertz sigma, but we have a way to do a room temperature probing and which is accurate to about 25 megahertz of the qubit frequency. So we do have to make a lot of devices, wafers, but we could do a lot of the room temperature probing before we actually cool down the device. And we could bring it down to, say here, it's still 100 devices that we have to cool down to actually find a good collision-free device to make the 17-qubit device, which, yeah, you don't want to do that. So these were the surface code architectures. So from the experimental point of view, it's with the frequency collision point of view, let's consider a different architecture. So having 2 qubits per bus, that seems to be the way to go. And less coupling is better, but we could consider this heavy hexagonal lattice, where there are 2 qubits per bus. And if we just choose this red qubit as the control qubit and the black qubit as the target qubit, for every 2 qubit gate, there are only 2 other qubit frequency that can cause crosstalk. So they're either weight 2 or weight 3 coupling, but you could restrict the control to be the one that only has 1 extra spectator qubit. So considering this architecture, now this is the model prediction for a 27 qubit device. That's about like 3 of these rings is around 27 qubits. So now again, here is the yield of collision-free chip versus the sigma that we could have. Again, starting from way up here with the fabrication, from the 25 megahertz precision that we could get from the room temperature probing, now we are down to about 14 chips that we have to cool down. Then this is a little more realistic. Doesn't seem it's too difficult of a. It is still difficult, but it's not 100 chips that you have to cool down. Okay, so how am I doing in time? Okay, I'll try to go quickly on this. So the next part, this work is not done by me, and this work was done by theorists at IBM, Levi Chris Chamberlain and Wan Yu. Both Ted and Andrew are here, so if you have any questions, you should ask them. So they came up with this new hybrid code having this heavy hexagonal lattice in mind. So we basically went up to them and said, what can you do with this lattice? And this is what they came up with. So here to the left, this is distance 5 qubit layout of the heavy hexagonal code. So here, the yellow qubits are going to be the data qubits. And the black qubits are the ancilla qubits for one type of the X type of the gauge operations. And the white qubits are going to be either the flat qubits for one type of the gauge operations and ancilla qubit for the other type. So to the right, it's the exact same device, but just kind of drawn in a nicer way to understand us for code. So let's focus on this picture. So you have these 2 blue lines. So if you do these 2 weight 2 operations for the Z-type gauge operations, and the product of this gives you a surface code. It's just going to be like a surface code stabilizer. Whereas these X operations is the weight 4 operation gauge operations, and these 2 strips, the 2 columns of X columns, give you like a bacon shore type stabilizers, and I think people call these bacon strips. I don't know. Anyways, okay, and then so I also have some scheduling written here just to go into how the scheduling happens. So for the weight 4 X-type gauge operation measurement, there are 2 flat qubits, the white qubits 5 and 6, and they're used to detect a single fault resulting in a weight 2 data qubit error. And then for the second part, this is the weight 2 Z-type gauge operation measurement, and the product of either the product of the 2 columns, the product of the column of the X-type gauge operation or the 2 of the Z-type would give you the stabilizer measurement. And they have also come up with a decoder which uses the flat qubit information to correct errors up to the full code distance, and which provides better thresholds. And just talking about thresholds, I will just show you this logical X and Z error rates. To the left, this is on the logical X error rates, and because the Z errors, the Z checks types errors was sort of like it's just same as the surface code, you could get this threshold, which was around 0.45%. And comparing this to the weight, comparing this to surface code, I think it was about 0.67, so it's slightly lower, but not too much lower. So this is considering we actually would have 7 CNOTs and 2 rounds of preparation and measurements. So then for this logical Z error, since this is like Bacon-Shor type stabilizers, there's no threshold. And again, you can ask Ted and Andrew more about this paper, but this just came up on the archive last week, so I highly recommend looking this paper. Okay, so just a couple more minutes. I'll have a couple more slides and I'll be done. So let's think about this heavy hex distance 3 logical qubit design. So to make a distance 3 logical qubit, so distance 3 is sort of a magic number for this logic program. So we always start with trying to make this distance 3 code. That has been a goal for us. We need 19 qubits in the lattice, 9 qubits used as the data qubit, and 10 for ancilla. And physically, we actually just use this hexagonal lattice. We could so we have a 23 qubit device that could use it for a distance 3 logical qubit with this heavy hex design. And this is just a preliminary result. But we made this device. We have a couple of extra dangling qubits. So this is a 27 qubit device, out of which 23 would be used for a logical qubit. And we have an average T1, T2 of around 40 microsecond. And just counting at the collisions, we do have collisions. So this is the 7 types of collisions. We have several type 1 and type 5 collisions. But this is one of the first devices that we cool down. So we are very optimistic in finding a new device where we have good coherences and no collision. And just to show you just quickly, this is not from the previous device, but in the single qubit planar devices, we have shown that this is over time in the T1 measurement that we could get a good coherence. So this is, we have been continuing to push on making improvements on coherence, and we're observing these reproducibility times upward of several microhundred microsecond for T1, with quality factor greater than 7-8 million. So we think that we know how to do this on a multi-qubit device as well. So this, we're optimistic in actually getting bigger devices with these type of coherences. And I'll just have this conclusion up, and I'm going to end my talk. Thanks for listening.
Thank you. That was a great talk. I'm wondering, could you go back to the tomography of the 422 code? My question is, you went from the 2-stage echo to the 4-stage echo, and the performance got better, or for the tomography, like the acceptance probability was much higher, and et cetera. But the randomized benchmarking was worse. Could you comment on how is the RB of the CNOT gate connected to the fidelity of this tomography?
Yes. So with the 4 pulse, the sequence actually gets a little bit longer. So a lot of the RB result gets hit from the fact that it was not twice as long, but it got much longer. It's mainly because our single qubit gates was not as fast for this experiment. So just from the coherence limit, it gets a hit, and also you're adding additional operations on the spectator qubits. So the randomized benchmarking result is still only looking at the 2-qubit space. So even though I have the spectator qubits added in the 4-pulse sequence, the benchmarking is only looking at two of the qubits. And now, more recently, we're doing more rigorous our randomized benchmarking tests where we not only look at the two qubits that we are interested in, but also including benchmarking, including the qubits that are surrounding it. So, if you compare that, that might give you a kind of better number.
Okay, wonderful. I wonder if I could ask the next speaker, Nata, to come up and start plugging in, and that will give us time for another cheeky question if we're quick.
Hi, thanks for the talk. So I wonder, you say that your recent chips, you start to achieve coherence times, which I guess are like an order of magnitude better than before. So what's the trick?
Oh, so what I could say is that the result that I showed was from a planar device, and this was a test chip. But I'm afraid I can't say much about the fabrication, nor I'm the expert to discuss about this. But.
Okay, we might have time for another one, actually. Did I see another hand up? Over here? Okay.
Oh, yes.
So, Maika, very nice talk, but so this choice between, because you have the ability to either make fix z's more or fix x's more, I was surprised. So you have this choice in the this compass style code with these bacon strips, and you've chosen the side where it fixes x's better than z's.
So I actually was talking with Ted yesterday, and I was a little bit confused because I would have thought of flipping the z and x, but from theory point of view, please correct me, Ted, if I'm saying anything wrong. But doing the simulating it, using the bacon short type with x or z versus the other one as z or x does not make any difference. And experimentally, when we implement it,
You'll flip it.
we'll flip it.
Okay.
Yes.
Thanks.
Okay, well, I'm sure there are other questions, but perhaps we can hold those for the break. And so let's thank our speaker once again and welcome our next speaker, which is Latency.